Our last topic is stellar evolution, in other words, the life cycles of stars. But we can't talk about that until we understand some of the basic characteristics of stars. What I often get asked a lot is, how do we know? Stars are millions and millions and millions of miles away. They evolve over time frames that simply a human can't even begin to understand. Yet we have a fair amount of confidence to say that we know how stars will go from one type of star to another. And the answer is, how do we know anything? And that is, we analyze the light that stars give off, and then we make inferences based on what we understand light to do. So let's begin by talking about inferences. Before we can ever infer anything, we have to gather evidence. So evidence refers to the data that we directly collect. So observations, uh, measurements, computer images, telescopic images and data. So those are all direct things. In astronomy, most of the time what we're talking about is we measure the electromagnetic radiation that stars are giving off. Our telescopes not only can give us an image, but they can also take a lot of readings about the light that they're collecting. We then look at the properties of light that we know to be true on Earth, and we use those to make inferences, or in other words, conclusions based on the evidence we collected. It's really simplistic, but a good analogy is those sequencing diagrams you did when you were a kid. You can look at this picture, and because you know how snowmen are made and you know that snow melts, it's pretty easy for most people over the age of 7 to look at this picture and know that the first one are the characters making a snowball. The next one is the snowman completed. The next one is the sun coming out and getting warmer and the snowman starting to melt a little bit. And the last one is the snowman melting. We know that not because we observed all of that happening in real time, but we understand how snow works and snowmen are built, and we can infer that that was the sequence of events. So when we look at stellar life cycles, another example would be looking at an animal. You may not know what lions look like during different stages of their lifetime, but for most people, we can look at these images and know the order of what a lion looks like as it's going from being very young to being very old. Most of us recognize that the smallest one is probably the one that it was when it was born. And we see characteristics that we associate with being very young, like the really big eyes. And then as it matures, we see that it gets bigger and it starts to develop a little bit of a mane. The mane increases, it's at maturity, and then we see that there's characteristics that we associate with old age, like low in activity, a little bit of graying, and so we can assume that that is the oldest lion. Might it be true that this lion is older than that one? It just happens to look very spry? Sure. But most of our reasoning tells us that that is a sequence of events based on what we understand about aging. So we can apply those same ideas to understanding stars and how they change over time. Let's go back, though, to talking about our understanding of light, because in order to make any of those inferences, we need to understand light. So, you don't need to write this down, that's why it's in italicized, but a couple of background bits of information. So, energy can be in the form of electromagnetic waves. So, a wave is created when a charged particle, such as an electron, accelerates. In other words, speeds up or changes direction. When that happens, the change in motion causes the electric field around the particle to change. That creates changes in the nearby particles, which creates the wave. We refer to the electromagnetic spectrum because it describes the different types of waves given off by things that emit energy. And as we describe the different types of waves, we can associate them with different types of properties. So the spectrum refers to all of the different types that exist. So that radiation, in other words, that transfer of energy through waves, occurs as energy is radiated from fluctuating electric and magnetic fields, electromagnetic radiation. As I mentioned, it's measured in wavelength. The wavelength is described as the distance between crests of the wave. We denote it in equations when we do math with that upside down Y shape. That upside down Y shape is called lambda. It's a Greek letter. And just like we would use X, or we might use M for mass. And as I mentioned, we understand light pretty well because we can work with light on Earth. So because astronomers know how different types of electromagnetic radiation behave on Earth, we can then infer what they are like in space. In order to make those inferences, we have to gather evidence about different types of electromagnetic radiation. So we have lots of different kinds of telescopes that can collect different wavelengths of electromagnetic radiation. If we take a look, this is not from stars, but it's an example of what I'm talking about. Each of these 3 images were created using a different type of electromagnetic radiation. The one on the left, X-ray, shows us what the interior of our hands are, the bone structure and so forth. The one in the middle, the infrared radiation, shows us the heat distribution in our hands. And of course, the visible light shows us what it looks like. Each one of these gives us different things that we can conclude about. So, for example, we can conclude that this person does not have any broken bones. We can conclude what the bone structure is. Based on this person's hand in this particular picture, we can assume that this person is involved in working. The hand is dirty. We can tell by the look of the hand and the lines in it that it's not a young person's hand. So we can make assumptions about these, each one giving us different clues in the picture. In order to gather these bits of information on different portions of the electromagnetic spectrum, we need to be able to measure that. So our telescopes are equipped with different sensors that each one can detect different types of electromagnetic radiation. You're probably familiar with light telescopes. So those are the ones that collect images of visible light spectrum. So if you came to our nighttime viewing, that's just a basic invisible light telescope. Shoot it in the sky, you look at it. There are lots of other kinds. Radio telescopes usually are the ones that have the really big satellite dishes, and you find them out in the desert places. Other telescopes fly, so the SOFIA telescope flies above the troposphere so that it can collect data that aren't affected by Earth's heat distribution. And others of them are, of course, up and posted in satellites in space. And each one has different sensors that can gather those bits of information about the different areas of different wavelengths of electromagnetic radiation. As we see, the wavelengths is what differentiates the different types. So microwaves, for example, have a longer wavelength than visible light, but shorter than radio waves. If you take a look at the size, some of them are very, very long. So radio waves are measured in meters, which remember are about 3 feet. Visible light is measured in nanometers, which means in 1 meter there's a billion nanometers. So we're talking very, very small wavelengths. And to the very, very highest energy wavelengths are the size of atomic nuclei. So there's a great range in the length of the wavelength. Spectroscopy is the field of study in which we can analyze light to determine what the chemical giving off the light is made out of. The way that we do that is by shining the light through a prism. As it shines through a prism, you're probably familiar with the rainbow that gets created because of that. That happens because the light bends, and when the light bends, it separates the light into the different wavelengths. This is possible because the light travels more slowly through the prism. Because the amount that the light bends in the prism is affected by the wavelength, that's what makes it possible for us to see the different colors, and more specifically to get very precise information about the wavelengths given off by chemicals. Spectroscopes are instruments used to see this. They have a diffraction grating that works the same way as a prism. Spectroscopes are also able to make spectrographs, which are just kind of images or graphs of this information. When we look at the spectrograph, we see that spectral lines are created. A spectral line is a pattern of lines in the spectrum that are unique to the elements giving off the light. How the spectrograph looks, in other words, what the lines are, is determined by the particular method of the way the light is given off. So is the light absorbed or is it emitted? We just don't have time to get into the different reasons why spectrographs look differently. But just keep in mind that sometimes when you shine light, like plain old white light through a prism, you just see a rainbow. That's the continuous light spectrum. Other times, depending upon whether we're talking about absorption of the light or emission of the light, sometimes it's a rainbow with black lines in it, and other times it's black with colored lines. Both of these are the same pattern, it's just the inverse of each other. When a material is giving off light, it creates a unique pattern because its composition is made up of its own unique elements. Every element has a particular pattern structure based on where the electrons are. The way that it's not real crucial that you understand this in real depth, but essentially what happens is every element has a position where the electrons are typically found. When the electrons absorb energy, they move briefly to a higher state of energy. When they move to a higher state of energy, they eventually return back to normal. Actually, it's really quickly. And when they return back to their normal position, that difference in energy is the light that it's emitted, and that creates the lines. If we take a look, this might be a pattern given off by a particular element. This particular element has electrons. Some of them were jumped up just a little bit to a different energy level. Others moved a lot. We can see that the more it jumps up, the closer it is to the blue and purple side of the visible light. The less distance it jumped, the closer it is to the red side of the invisible light. That has to do with the amount of energy it's given off. That specific pattern is very much like a barcode that you would find at the store. When you go to the store, you take your item to the checkout line and the cashier scans it. And that barcode that's on the checkout line tells the computer what the item is and how much the store is charging for it. That's because that pattern of lines that we see, where there's a thick line, where there's a thin line, etc., is something the computer can read as unique. The pattern of lines given off by elements is also something that a computer can read as unique and say, hey, that pattern belongs to this element. So since every element has its own unique pattern, we can look at the lines in a star and say, hey, that pattern's in the barcode, that pattern's in the barcode, and identify what elements are there. So here are some of the common ones. We'll look at this in lab. When we look at sunlight, it's of course more complicated than this because they're not just made up of one single element. There are things that are more common, obviously, like hydrogen and helium, but we see lots. And so it's necessary for, when we get a barcode that looks something like this is just a portion of it, it's necessary for a computer most of the time to do the analyzing. If we take, though, we can see that there's a small amount of iron in the sunlight because here's the light emitted from the sun on top. The iron pattern is below, and we see that every line that exists in iron also exists in the patterns in the sun. If we take a look at this example, really simplified, the top image is the pattern that we're observing from the star. And if we look, A, B, and C represent different elements that might be in the star. Take a moment and see if you can figure out which of these elements is in the star. You guessed B, you are correct. And when we look at B, every line that's in B is also found in the star. Whereas A, there's a lot of them that are similar, but there are some that are different. So, for example, the star does not have a thick line right next to this big thick one, nor does it have these two thick lines up here. If we look at C, we also can find that there are some lines, for example, this thicker one, that's not found in the star. So the only element of these three that's in the star is the element labeled B. In addition to spectroscopy, we can find out a lot about the star simply by knowing its wavelengths. The first thing we need to figure out is what are the dominant wavelengths that the star is giving off. So stars, as I mentioned, are giving off lots of different wavelengths. But as we analyze it, we can see that there's always going to be one wavelength that is emitted the most brighter. In other words, has the largest percentage of energy that's emitted at that wavelength. We call that wavelength the dominant wavelength, and in formulas and things like that, we call it lambda max. Since we're not going to be doing any math with this unit, you won't have to worry about that, but you'll see it in some graphs. The dominant wavelength then is used to describe the characteristics of the stars. For example, we can use the dominant wavelength to identify the surface temperature of stars. When we analyze the light, we see that the dominant wavelength corresponds to different characteristics that we have observed on Earth. Generally, we find that the shorter the wavelength, the more energy the wavelength is carrying, the warmer the temperature is that's associated with that amount of energy, and the greater the frequency. In other words, the faster the wavelength is moving. Frequency, just an FYI, is the number of waves per second. In other words, it's a method of describing how quickly the wave crests are coming. You'll notice that each one of these is associated with a law. And then I put that up there because I know a lot of you will say, well, how do we know that? That's because there's been whole fields of research to associate this with laws. As I've already mentioned, different colors are different from each other because they have different wavelengths. Blue light has shorter wavelengths than red, and we notice within the rainbow of colors, anything close to red, such as yellow or orange, is going to have a longer wavelength than anything close to blue, which is going to have a shorter wavelength. Because those colors nearest blue then are going to have shorter wavelengths, based on the last slide, we can see the colors, wavelengths and colors close to blue are going to be hotter, more energetic, moving faster, and generally will be brighter. You observe this phenomenon when you've seen a metal heat up. So you might notice that sometimes we say that, oh, it's red hot. That usually means that it's hot enough to glow. But if you watch a metal heat up, it glows red first, and as it gets hotter and hotter, it then changes color into yellow and eventually white. And so that change in color from red to yellow is indicating it's getting hotter and the wavelength is getting shorter. To determine the dominant wavelength, we need to look at what wavelength is that the star is emitting is the brightest. So we make a graph of brightness versus wavelength. We happen to call that graph a black body curve. It's not something I'm going to ask you about. So these three curves represent black body curves, or in other words, all of the wavelengths given off by a particular object. The crest of the curve, so the peaks up here and here, all correspond to the dominant wavelength. So the top line is peaking somewhere around 400 nanometers, which is associated with temperatures in the range of 7,500 Kelvin. We can see then that the middle line is just below 500 nanometers, and that's associated with the green range of light, so that star probably would look green, and it has 6,000 Kelvin. Since we have this relationship between wavelength, energy, and color, we can classify stars that way. All stars have hydrogen in them, so we look at the strength of their hydrogen lines. They were originally listed as A, B, C. Astronomers later on decided to reorder them based on their temperature because it was more informative than their hydrogen content. And so then those ABCs then got rearranged into this weird sequence of O, B, A, F, G, K, M. Obviously that sounds really, really random, and so there's a memory trick, and that's O, be a fun guy or gal, depending upon your interest. So O, be a fun guy, kiss me. And O being the hottest, the M or the me being the coolest. They can further be grouped by their size. We'll get into that later. So generally when we look, the stars, Rigel, for example, is one of the hottest stars that we can see from Earth, and that's in the B range. Betelgeuse, as you know, is very close to supernova. It's actually a red supergiant. Its color is red, and so you'll notice that that's in the coolest spectral class. Another characteristic of stars that we need in order to make conclusions about stellar properties is its magnitude. Its magnitude describes how bright an object is. There are two kinds. The first one is how bright it appears to be from Earth, and the second one is how bright it actually is. The apparent magnitude is affected by distance. So if you recall the inverse square law, energy spreads out as you get further and further away. So consequently, the brightest object in our sky is the sun. It's only the brightest object because it's close. So when we analyze apparent magnitude, the star that looks the brightest in our sky, in this diagram it's number 3. When we put them all in the same distance, we notice that number 3 isn't particularly notable, it's just closer. Comparing the stars to how bright they actually are without the effective distance is called absolute magnitude. Absolute magnitude compares the actual brightness of stars, ignoring the effective distance. So astronomers just chose a random distance, 10 parsecs, and said, okay, how bright would these stars be if they were all at 10 parsecs? And at that distance, our sun doesn't remotely stand out. This is also a measurement of the star's luminosity. Luminosity is really just another way of describing brightness, relating it to how much energy is given off per second. For our benefit, brightness, magnitude, and luminosity are going to be used interchangeably because we're just not getting that specific. So why do we care about all of this? Well, we care about all this because they allow us to group stars and determine where they are on their evolution. The way that we do that is using something called an HR diagram, or Hertzsprung-Russell, just named after the people that came up with it. And so an HR diagram is a graph that compares the luminosity or brightness of a star to the temperature of the star. Being able to place a star in the HR diagram allows us to identify lots of patterns and characteristics of the stars, including its temperature, its size, its mass, its color, its age, its spectral type, and most importantly, what stage of development it is. We'll get there in our next section. We're going to do an activity regarding the HR diagram, so skip ahead in your notes to the next section, and we'll come back to this in class. The very last thing I want to talk about is how we determine a star's motion. To determine a star's motion, we use a phenomenon known as Doppler shift. You might have heard the word Doppler before in weather forecasts when they talk about Doppler radar. Doppler just is a way of analyzing the movement of something. In the case of weather, it's the movement of the raindrops. In our use, we're going to be analyzing whether a source of light is moving. When the source of light moves, it affects how we see the wavelength. Because each successive wave is emitted from a different position, the wavelength looks either longer or shorter. This allows us to determine whether the star is moving towards us or away from us, and at what rate, or in other words, the velocity. Rather than take time to explain this diagram, I want to show a quick video.
The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future.
Just to quickly summarize and get in your notes what the video said, blue shift, which they didn't talk much about, occurs when the source of light or sound or whatever is moving towards you. And so each wave is emitted closer and closer and closer, and as they said in the video, they bunch up, or in other words, they appear shorter than it actually is. In other words, it appears shorter than it actually is, which makes them shift slightly. I mean, it's very imperceivable without technology, but it shifts slightly towards the blue side of the visible light spectrum. Redshift, conversely, is, as they said in the video, when the object is moving away from the observer, and so the waves appear to be stretched out. The wavelength is then a little bit longer, or in other words, shifted just slightly to the red direction, or a redshift. So when we look at, say, the spectrograph of a star, we can see that this star very clearly matches up with this pattern below it, but everything is just mildly shifted in one direction. In this case, it's shifted towards this side, or in other words, the red, and so this is a red shift. Our telescopes can detect these minute changes, and when I say minute, we're really talking about like tenths of nanometers. So really small changes, but our telescopes can detect it, and from that we can conclude what objects are doing, and we see that most of them are moving away from Earth. So this tells us all kinds of stuff, including the direction of movement. That we can also calculate how much the shift is to determine how quickly it's moving. We can look at the sun and see the movement of the gases within the sun. We can look at star systems that have two stars orbiting each other, and as they do, we can see which one's coming towards us or away from us. Probably the most important thing Dr. Schiff can tell us is when we look at the universe as a whole. So for this, we typically look at other galaxies because the individual stars we see are within our galaxy and they're orbiting a central point. But when we look at other galaxies, like the Andromeda Galaxy, we see that all of the light coming from the other galaxies have red shifts. And so consequently, astronomers use that for the basis of the Big Bang Theory. In other words, that the universe is getting further and further away from us, or in other words, further and further away from everything else. That's it for this section of notes. Our next section will be on the evolution of stars. As always, come see me if you have questions.